chapter 8, we're going to encounter a lot of different reactions where we're adding compounds to the double bond in an alkene. Now, starting with this chapter, and really throughout the rest of this semester and in the second semester, we're going to encounter a whole bunch of reactions that you need to know. And so one of the things I'm going to recommend is to make a reaction notebook. And so every time we encounter a new reaction, you'll add it to your notebook. And you'll have the reaction, you can add the mechanism, you can add information about its regioselectivity and its stereoselectivity. And I think by keeping this reaction notebook, it'll help you to learn these reactions and to keep them straight. In the last chapter, we studied elimination reactions of alkyl halides. In this chapter, we're going to study essentially the opposite reaction, where we're adding compounds to the double bond in an alkene. Now, addition and elimination are in many ways opposite reactions, and they're connected by an equilibrium. Which side is favored depends on the temperature. So it turns out that addition reactions are exothermic. So the forward reaction in this scheme is exothermic, and so delta H is going to be negative. Now, I think you can also see that for the forward reaction, delta S is also negative because we're going from 2 moles of reactants to 1 mole of a product. And so delta S is going to be negative, and so negative T times delta S means the entropy term is going to be positive. And so when we think about delta G needing to be negative for a process to be spontaneous, we can see that for an addition process, at low temperatures, when the entropy term is not important and we just focus on the enthalpy term, the reaction is spontaneous. But as the temperature increases, the entropy term is going to become more important, which is going to contribute to a positive delta G. So high temperatures favor the reverse process. They favor elimination. So if we want to prefer the addition reaction versus elimination, we want to use low temperatures. So high temperatures favor elimination, whereas low temperatures favor addition. The first addition reaction we're going to study is hydrohalogenation, where we're going to add an HX molecule to the alkene. And so we can use HCl, HBr, or HI. And so in this reaction, which we conduct at low temperatures because low temperatures favor addition reactions, the hydrogen is going to add to one of the carbons of the double bond, and the halogen is going to add to the other carbon. Now, this alkene is symmetric, and so which side gets the hydrogen and which side gets the halogen doesn't matter. We're going to get the same compound either way. But if the alkene is not symmetrical, then we're going to get 2 different regioisomers, right? One where the hydrogen adds to the more substituted carbon, and one where the hydrogen adds to the less substituted carbon. And so the question is, where does the hydrogen and where does the halogen go? So the rule that we have for hydrohalogenation is called Markovnikov's rule. And this says that the hydrogen adds to the less substituted carbon, and the halogen adds to the more substituted carbon. And we're going to study the mechanism later on in this video to explain why we see Markovnikov addition, where the halogen adds to the more substituted carbon. Now, it is possible to cause reactions to prefer anti-Markovnikov addition, where the halogen actually adds to the less substituted carbon. And we can typically do that by adding peroxides to the reaction mixture. And so if we just add HBr, we'll get Markovnikov addition. If we add HBr, but in the presence of a peroxide, where we have an oxygen-oxygen bond, then we get anti-Markovnikov addition. Okay, so we have 2 examples here, and so we want to predict the major product for each of the following reactions. So in the first case, I'm just adding HBr. I don't have a peroxide present, and so this should follow the Markovnikov addition. So the bromine should add to the more substituted carbon, and the hydrogen will add to the less substituted carbon. And so in this case, my product would be this. In the second example, I'm adding HBr again, but now in the presence of a peroxide, the halogen should add to the less substituted carbon. So we would expect this to be our major product. The mechanism for hydrohalogenation is a two-step process. It starts off with a proton transfer where the pi bond in the alkene ring attacks the hydrogen. That moves the bond from the HBr to a lone pair on the bromine, and then that's followed up by the bromine acting as a nucleophile and attacking the carbocation that's produced in the first step. If we look at the reaction energy diagram for this process, we can see that the first step, the proton transfer, is the rate determining step. It has the higher of the two activation energies. All right, so if you recall, there are two possible products. We can have Markovnikov addition, where the halogen adds to the more substituted carbon, and the anti-Markovnikov addition, where the halogen adds to the less substituted carbon. And so in order to have anti-Markovnikov addition, when the pi bond attacks the hydrogen, if the hydrogen goes to the more substituted carbon, then we get the carbocation on the less substituted carbon. Whereas for the Markovnikov pathway, when the pi bond attacks the hydrogen, we end up, if the hydrogen goes to the less substituted carbon, then we end up with a carbocation on the more substituted carbon. And so when I compare these two intermediates, we can see that this intermediate is going to be more stable with the tertiary carbocation as opposed to the secondary carbocation. And so the mechanism explains why Markovnikov addition is preferred. All right, so in this example, we want to predict a major product and draw the mechanism for the following reaction. And so this should be Markovnikov addition because I'm just adding HCl. I don't have any peroxide that would indicate an anti-Markovnikov addition. So the chlorine should add here, the hydrogen should add here, and so my major product should be the following. All right, and if they want us to draw the mechanism, let me redraw our starting molecule. So when we add HCl, the pi bond will attack the hydrogen. The bonding electrons will move on to the chlorine as a lone pair. And so the hydrogen is going to go here. We don't necessarily have to draw that, but I'll go ahead and do that. Then the carbocation ends up here. We then have our chloride ion will undergo nucleophilic attack and give us our final product. So the last thing we want to consider is the stereochemistry of hydrohalogenation. And so hydrohalogenation may result in the formation of a chiral center, as we have in this case, right? We've got a methyl, an ethyl, a chlorine, and then the hydrogen that we're not showing. And so then the question is, which of the two configurations are we going to get? Are we going to get the R or the S? And so it turns out in hydrohalogenation, we're going to get both products, generally in equal amounts. And so this reaction would have two products. We'd have the R and the S. And so when we form the carbocation intermediate, it's basically planar. And so we have this empty p orbital, and so we can attack with the nucleophilic attack from either side of the planar carbocation, and so we get both of the configurations in relatively equal amounts.